Exercise 2.1. Consider r of x equals 3x squared plus 2x minus 1 divided by x plus 2. Then, for x not equal to 0, we have that r of x is equal to 3x plus 2 minus 1 divided by x over 1 plus 2 divided by x. Now observe, as x tends to infinity, 1 over x and 2 over x both go towards 0. So this thing and this thing both go towards 0. So why doesn't r of x go towards 3x plus 2? So pause the video and play with this a little bit. I mean, if you don't believe me, we can see the graph of it right here. This blue line is the line y equals 3x plus 2. The green line is the line y equals 3x plus 4. And the red line, or the red curve, is the function r of x. And we can clearly see that r of x is getting closer and closer to y equals 3x minus 4. So pause the video and have a go at answering this. Note that it's very easy to prove using polynomial division, but I would like an intuitive explanation as to why this thing doesn't go towards 3x plus 2 as x tends to infinity. Okay, let's work on this together now. So first of all, let's prove using polynomial division. So going ahead and just using polynomial division here, x plus 2 into 3x squared plus 2x minus 1. Okay, so 3x squared plus 6x, and then subtract, and we get minus 4x minus 1, so then minus 4. And so minus 4x minus 8, and then our remainder is 7. So that tells us that r of x is equal to 3x minus 4 plus 7 divided by x plus 2. And so clearly this thing tends towards 0 as x tends to infinity, and so the function r of x tends towards 3x minus 4. And we're going to look at this in a couple of other ways as well. First of all, we can also note that we don't really need to deal with this minus 1, because if we split this thing up, so it was 3x squared plus 2x and then minus 1 divided by, gosh, I already forgot, x plus 2. We can immediately split this up into 3x squared plus 2x divided by x plus 2 minus 1 divided by x plus 2. And since we're looking at the limits as x tends to infinity, clearly this thing goes towards 0 as x tends to infinity. So it must be this thing here that goes towards 3x minus 6 as, 3x minus 4 as x tends to infinity. And again, we still have the same situation. 3x squared plus 2x divided by x plus 2 is equal to 3x plus 2 divided by 1 plus 2 over x, for x does not equal 0. And I mean, we could do the same polynomial division argument to show that this thing really does go towards 3x minus 4. But let's look at it in a different way this time. Let's actually use limits. So 3x squared plus 2x divided by x plus 2. If this thing was to get closer and closer towards 3x plus 2, then when we subtract 3x plus 2 from this, the limit as x tends to infinity of the whole thing should equal 0. But actually working it out, we get, well, 3x squared plus 2x, and it's going to be minus 3x plus 2 times x plus 2, and then the whole thing is divided by x plus 2, and then this is equal to the limit, oops, I forgot my limit here, limit as x tends to infinity, so the limit as x tends to infinity of 3x squared plus 2x minus 3x squared plus 8x, and then plus 4 divided by x plus 2, which is equal to the limit as x tends to infinity of 3x squared plus 2x minus 3x squared minus 8x minus 4 divided by x plus 2, and then that goes away, and we are left with the limit as x tends to infinity of negative 6x divided by, negative 6x minus 4 divided by x plus 2. And to figure this out, limit as x tends to infinity, we can make it negative 6x minus 12 plus 8 divided by x plus 2, just to get rid of that fraction. Well, the fraction with x's in the denominator and numerator anyway. Alright, and then that's equal to the limit as x tends to infinity of negative 6, because we can factor negative 6 out of there. So negative 6, and then just plus 8 divided by x plus 2. And then clearly as x tends to infinity, this one goes towards 0, so the whole thing is just negative 6. And we should have known that immediately, just because, well, looking at the difference between 3x plus 2 and 3x minus 4, well, they are 6 apart. And so what it's saying is that whatever this rational function here, 3x squared plus 2x divided by x plus 2, it's going to get closer and closer to 6 less than 3x plus 2. And 6 less than 3x plus 2 is exactly 3x minus 4. So yeah, it seems to agree with our graph here. As far as 3x plus 2, this green one is 3x minus 4. But the original question I asked you guys was about the intuition of this, because, I don't know, maybe it really does look like this thing gets closer and closer to 3x plus 2 as x tends to infinity. So let's talk about the intuition now that we have proved that it definitely doesn't. Alright, so first of all, and we already kind of noted this, the whole 3x plus 2 minus 1 over x divided by 1 plus 2 over x can be split up into two parts here. And we observe that the 1 over x divided by 1 plus 2 over x is equal to 1 over x plus 2. That tends towards 0 as x tends to infinity. So we don't really need to pay attention to this part too much. What we do need to observe is that this part here tends towards 3x minus 4, not 3x plus 2, as x tends to infinity. And so that's what we're gonna talk about. And the idea is as follows. Even though 2 divided by x tends towards 0, so even though we got 2 divided by x going towards 0 as x tends to infinity, 1 plus 2 divided by x is bigger than 1 for every value of x. So this thing on the bottom is bigger than 1 for every value of x. That's important. And that tells us that 3x plus 2 divided by 1 plus 2 divided by x is strictly less than 3x plus 2 for every value of x. So that's a good starting point to really comprehend what's going on here. Secondly, observe that even though 2 divided by x is going towards 0, 3x is going towards infinity also. And the rate of decrease of 2 divided by x is not enough to completely compensate for the rate of increase of 3x for large values of x. We can think of it as a sort of catch-up game. So the 1 plus 2x is lagging behind where it would need to be before the entire fraction can approach 3x plus 2 as x tends to infinity. So the one on the bottom is always kind of too much bigger than 1 for where it would need to be at each particular value of x, considering the fact that 3x is going towards infinity before this entire fraction could approach 3x plus 2 as x got larger and larger. Now let's generalize it a bit more. Remember we were dealing with 3x plus 2 divided by 1 plus 2 over x. So that's what we were looking at before as x tends to infinity. Alright, so note that ax plus b divided by 1 plus d divided by x tends towards ax plus b minus ad. So that's the constant. So it gets closer and closer to a line, but instead of b, we have b minus a times d as x tends to infinity. You can prove this using polynomial division. And so that means that the bigger values of a and d result in an oblique asymptote that is further away from y equals ax plus b, because the values of a and d, well, control, I guess, the rate of increase of the ax part, and I guess the rate of decrease of the d over x part. So yeah, the bigger values of a and d result in an oblique asymptote that is further away from y equals ax plus b. Whereas if we make them smaller, then it's going to get the asymptote that the whole thing gets closer and closer towards, gets closer and closer towards ax plus b. And this makes sense as a bigger a results in a faster increase of the ax plus b part, so the numerator. And when I say faster, I mean that ax plus b is bigger for any given value of x than it would be if the a part was smaller. While a bigger d value results in a slower decrease in 1 plus d divided by x. So what I mean by a slower decrease in 1 plus d divided by x here, 1 plus d divided by x is further away from 1 with a bigger d value for any given x than what it would be with a smaller value of d. Okay, so that really is the intuition behind it. The one on the bottom is not getting to 1 fast enough to compensate for the fact that the one on the top is growing bigger and bigger, and as a result of that the whole thing does go towards a line, but the line is slightly less than what it would be, slightly less than ax plus b, which is what it might look like it's heading towards at a first glance, just because that thing goes towards 0. I've written a little bit more down here, just kind of for interest. So it's interesting to note that ax plus b divided by 1 plus d over x squared does tend towards ax plus b, as x tends to infinity. And you can pause the video and prove that just using, well, however you like. I've got a proof down here. Let's take a look. And there is, well, one way to show that is just to say since ax plus b divided by 1 plus d over x squared minus ax plus b, which is the same as ax plus b times 1 plus d over x squared divided by 1 plus d over x squared. If you actually do that multiplication, everything cancels down to this thing here, minus bd over x squared minus ad over x divided by 1 plus d over x squared. And clearly that tends towards 0 as x tends to infinity, because simplifying it down, we can write it as negative bd over x squared plus ad over x divided by 1 plus d over x squared, and then multiplying the top and the bottom by x. Go over here because I'm going to run out of room. This is negative ad plus bd over x divided by x plus d over x, and then clearly that goes towards 0, that goes towards 0, and then since we still have an x over here, the top part is going towards ad, the bottom part is going towards x, and that's going towards 0. So the whole thing goes towards 0. And so what this tells us is that d divided by x squared goes towards 0 at an appropriate rate for the entire function the entire fraction, function, whatever, the entire fraction ax plus b divided by 1 plus d over x squared to approach ax plus b. Whereas that was not the case for when we had ax plus b divided by 1 plus d over x. In that situation, the d over x went towards 0 too slowly for the whole thing to get closer and closer to ax plus b. Right, that'll do.